This is crazy.
If you're gonna feature the moose ears, you gotta like center yourself on there. Or deer antlers, what are they? I don't actually know, but you gotta center yourself so it looks like they're coming out of your head. Yeah, teach class like that.
Okay, I got something to say. No. Yeah. Let me go back to there's my first slide. Okay, yeah, I can't center myself on the antlers behind me, but how is everyone doing? I just want to kind of make sure the chat part of this is working, or not the chat part, but moose ears. Yep. Okay, all right. I guess I'm muting Alex for now. RIP headphone users. What?
Earlier when you had both of yourselves unmuted, the little like ding ding that Zoom does happened, and then it echoed itself between, I think, the two of them, and it made a disgusting high-pitched noise that hurt everyone.
It was very disgusting.
Yeah, I'm sorry. I'm very sorry about that. I will try not to do that in the future, but no guarantees. We only got to put up with 2 of these or 3 of these. So at any rate, okay. It's 5:01. Are you guys ready? I am not ready at all for this, but we'll see how it goes. Oh my gosh, let's get rid of all this. Okay, so are there any questions before I get started with today's new material?
Alex, did you come up with anything about the multiple degenerate subsystems?
Not yet.
All right.
But I promise
Cool.
I'll work
Thanks.
on it. Other questions? Okay, all right. So Ross is connected, and let me count 1, 2, 3, 4, 5, 15, 16. We're missing at least one person, but I guess they'll sign in eventually. All right, so what we're going to do today is very interestingly, surprisingly interestingly to me, it's overlapping with what Laith Haddad has been doing recently, I think, in his graduate classical mechanics course, which I should say is something that he should not be doing in his graduate classical mechanics course, but there's no stopping him. At any rate, I know that Laith has touched on Green's functions. I do not know to what depth or even really to what use, but I know he's doing them. So I am going to take you on a walk through Green's functions. We're going to work in 1 dimension today, get the basics laid out, and then on Thursday we'll move up to 3 dimensions, and that will largely flesh out our story between this Thursday and next Tuesday. Seth asked that I have the exam ready next Tuesday after class is over, and I'm pretty sure I can do that. So your take-home final will be available after class is over next Tuesday.
Hey, Alex.
Yeah.
You have homework 9 posted as due tomorrow. Did you mean Thursday or Tuesday next week?
I meant Tuesday of next week. I screwed up. Sorry about that. Yeah, I probably just looked at the calendar and picked a Tuesday, and so the homework is due. The homework is due next Thursday. Okay, so let's get started. Okay, so just let me know if some of this is crappy. So Green's functions are essentially, one way to view them is they're a means of transforming a differential equation into an integral equation. And sometimes this is easy. So we could, for example, start out with a differential equation that looks like this. Okay, can everybody see that all right?
Yep.
Okay, good, thank you. But and in this case, if we have, say, a boundary condition that y of a is equal to y naught, then this is very easy to solve because all we do is we just move that dx over to the other side. And then we integrate both sides. Okay. So well, what can Green's functions do that you can't do with that? Well, it turns out that you can't always do this in such a simple fashion. For example, I might give you a differential equation that takes the following form. Okay, and this is going to make it rather challenging to do this sort of simple integration technique, or I could give you a more complicated differential on the left-hand side. I could do dy dx plus x squared d2y dx squared. Oh, okay, my pen is screwing up on me. Oh my goodness, my handwriting is going out the door. Okay, so both of those equations don't really lend themselves to the simple integration technique that we have in the first example. So Green's functions are going to actually take care of these. And so we're going to spend some time developing this from the ground up, and then we'll see applications of it throughout. So to get started, and let me see, I guess I'll just erase, yeah. Maybe I shouldn't be erasing, but I'm going to erase anyway. And maybe I can erase everything. There we go. Okay, so what we're going to do is we're going to start out with an equation which can be written as some linear operator acting on the function y, and that's going to be equal to some function of x, okay? And the linear operator L can be written in general as some coefficients and this is going to be acting on y, so this would actually be Ly. It's going to take me a little bit of time to get used to, but once I get used to it, I'll just fly through these. So okay, so that's the form of L, and then f is some given function of x. Now, what we want to do is we want to consider that L possesses a complete and orthonormal set of eigenfunctions. So we know that that means that L acting on an eigenfunction is equal to the eigenvalue corresponding to that eigenfunction times the eigenfunction itself, okay? But if the set of eigenfunctions is complete, which we're going to assume in this context, then that means that we can expand both the unknown function y of x, which we're trying to solve for, we can expand that in terms of the eigenfunctions. So we might have some from n equals 1 to infinity of alpha n phi n of x. And we can also expand the given function in the differential equation f of x in terms of these as well. Okay, now we're going to shove those into the differential equation that we're trying to solve, and we're going to do some manipulation using the ideas that we have from manipulating an orthonormal basis set. So if I shove these in, I'm going to have Ly, and let's start by using the Ly. So this is going to be L acting on the sum of alpha n phi n of x. Of course, L can go inside of that sum. Now, if I let L act on the phi n, then I'm just going to grab the eigenvalues times phi n. So this is going to be sum from n equals 1 to infinity of alpha n lambda n phi n. Okay, and then If I shove in the expansion of f, then of course this is going to give me sum n equals 1 to infinity of beta n phi n of x. Now I can take these two expressions and I can easily extract a useful expression. That is the sum from n equals 1 to infinity of alpha n lambda n minus beta n times phi n equals what? Is he there?
0.
It is 0, but Josh, that wasn't you. I'm so disappointed. He was glowing just a minute ago, but thank you very much. That's equal to 0. Okay, now, wait a minute. If this is a complete set of eigenfunctions, and this is equal to 0, what can you tell me about this?
It has to equal 0.
This has to equal 0 as well. Okay. So what we have is that alpha n is equal to beta n over lambda n. Okay. And now we can write our expansion of y of x as the sum from n equals 1 to infinity of beta n over lambda n times phi n of x. Okay. Now recall that beta n's are given by the inner product of phi n with the function f. Okay. Again, this is a standard part of the story of linearly independent orthonormal sets of eigenfunctions. Therefore, y of x can be written as, and man, yes, okay, here we go. There's something so different about walking around with my notes in my hand, staring at them in my face versus trying to keep them on the table out of your sight so that I can, it's really crappy. But anyway, I'll get used to it. Anyway, plugging in the expansion in terms of the inner products, what we're going to have is that y is the sum from n equals 1 to infinity of, goodness, 1 over lambda n times phi n times the inner product of phi n with f. But this, if we remember what the inner product is, it's just an integral. So swapping the integral with the sum, we can do the integral from a to b, where that's the interval over which we've defined our inner product, sum n equals 1 to infinity of phi nx phi star n of x prime all over lambda n times f of x prime dx prime. Okay? Well, that's kind of interesting. This thing right here under this integrand on the right is what we call the Green's function. And the important thing to note is that this thing is built out of the eigenfunctions and eigenvalues of the operator L. It doesn't depend on F. It's being integrated with F on the right-hand side, but that function itself only depends on L. Now, it's kind of interesting. So how many of you have seen this before? Give me a show of hands. 1, 2, 3 of you. Okay, 4 of you, 5 of you. Okay, six of you. Okay, all right. So I'm teaching the half the class. The other half, you can just, go take a coffee break or whatever and come back when we get to something that you haven't seen before. But at any rate, what I want you to first consider before we talk about the utility of this is L times G. Let me lower that a little bit. L times G of x prime. Okay, so this is often labeled as gx x prime. Okay, so if we take L acting on gx prime, then that's of course just going to be the sum from n equals 1 to infinity of L times phi n of x, phi n star x prime over lambda n. Okay. What's that going to be equal to?
It's going to be a delta function.
It's going to be a delta function. Actually, that's not going to be a delta function yet. This is going to be the sum from n equals 1 to infinity. Oh my goodness. From n equals 1 to infinity of, well, L acting on phi n is just going to give me back the eigenvalue times phi n, but the eigenvalues are each going to cancel with the eigenvalues in the denominator. So this is just going to be phi n of x. Goodness. All right, my pen is bleeding. Go away. There we go. Phi n of x, phi star n of x prime. And this is something we can call the identity between x and x prime. Okay? Now, what is useful about that is that if we do an integral from, oh my goodness, from a to b of I x x prime, f of x prime, oh my goodness, this is going to be painful. Then this is going to be the sum from n equals 1 to infinity of phi n of x, integral from a to b of phi n star of x prime, f of x prime, dx prime. But this is going to be the sum from n equals 1 to infinity of phi n of x times the inner product of phi n with f. What is that last term equal to?
F of x.
Yes, that's equal to f of x. Good. Well, wait a minute. Look at this and look at this. What do you think the I is playing the role of? Now, Ross, you can shout out your answer.
Delta function.
Yes, thank you very much. So I is playing the role of a delta function. Relating x and x prime. Okay, so what we have is that if we have a linear operator L and we act on the Green's function with it, then this is giving us a delta function. And so there is a certain sense in which you can imagine, and I'll put this in parentheses or in quotes, you can imagine that G is in some sense L inverse. Okay. Now there's a more formal way to write that down. It involves redefining an operation K, which is the integral of the Green's function with whatever you're acting on, but we won't worry about that. Right now, what we want to do is we want to move on to some examples of actually calculating the Green's function. And then at the end of each calculation, we'll verify that it does in fact satisfy this inverse requirement of acting on the Green's function with the linear operator in question gives us a delta function. Are there any questions before I move on? Okay, all right. I'm actually going to take my watch off and I'm going to set it in front of me so that I can see what time it is so I don't run over. Okay, so let's start with a simple example and one that I know you're going to know the answer to. So let's start with d by dx as our linear operator. So we have that we want to act on a function, unknown function y, and we want to drive that with some function f of x. And what I'm going to do is I'm going to give you a boundary condition equivalent to what we worked with before, so that y at a is y naught. And then we know the answer to this story from what we talked about before, and that's just that yx is y naught plus the integral from a to b of g of x prime fx prime dx prime. And we can compare this to the story that we played out before, which was we talk about d by dx of y is f with ya equals y naught. And if we just do the integral, then we have that y of x is y naught plus the integral from a to x of x f of x prime dx prime. Okay, now here we want the x to sit on the interval from a to b. Well, these two things are very close. So up here, we've got the integral from a to b. That's over the entire interval that x sits on of the Green's function times the function itself. We have the integral of that, and this should reduce to this expression here. How are we going to manage to do that? How are we going to define a Green's function which basically equates this integral to this integral? This is the simple situation where we already know the answer. We're eventually going to get to situations where we don't know the answer. So we want to get the answer to what the Green's function is from insight. So what do you think the Green's function might be in this case?
I kind of want to, I kind of want to say it's 1, but since we're going from from A to B and then from A to X, I don't know how that translates there.
Any other guessers?
I think it's going to be a theta function.
A theta function, yeah, it will be a step function. So it turns out that if we write this as y naught plus the integral from a to b, okay, a to b is a larger interval than a to x. X is a point, you know, somewhere in the domain of a to b. But if we do it over the entire interval from a to b and we add in a theta step function, then now we have it. And if you don't remember what the step function is, the step function is simply 1 if x is larger than x prime, and it's 0 if x is less than or equal to x prime. Okay? Are we on board?
Wouldn't we want this to be like the other way then, because we're trying to get rid of the interval from like x to b to make it the integral from a to x? Like, what would we want, like the plus x prime instead of minus with that or something? Does that, does my question make sense? That it seems like if it's 1 before, or yeah, it's like it goes from 0 to 1, then that seems like it would make the integral from x to b the one that does not go away.
So let me look for a second. So it's 0 and x is less than x prime.
So that would make like the integral from a to x 0, right?
You're right, I believe. Let me check my notes.
Can I weigh in?
Yeah.
So actually, in the interval from a to x, if x prime is between a and x, and that means x is greater than x prime. Now, I guess at x it will be equal to, but that's just 1 point, so it doesn't matter. So actually he had it right with theta of x minus x prime, because in the left interval from x prime equals a to x is greater than x prime.
Yes.
So then theta makes that 1. Whereas in the right interval, when x prime is between x and b, then we get x prime is greater than x, or x is less than or equal to x prime, which then means that the theta function is 0.
You follow that, Madison?
I think I'm gonna have to stew on it for a second, but I trust you. I trust both of you that that makes sense, and I'm just thinking backward.
Okay. All right, pressing on a bit. So Mr. Bean is going to make the simple observation of what is our Green's function?
Our Green's function.
In this case.
Sorry, I'm getting water at the moment. Got to stay hydrated.
Awesome, sweet. You better hurry. You better run. What is
Anyway, so our Green's function would just be the theta function.
Exactly, it's the theta function. Okay. Well, hold on. Let's check and make sure this makes sense. If that is genuinely the Green's function, then if we act on the Green's function with the linear operator that we use to define it, we better get a delta function. Well, let's think about it. So we want to take the linear operator is just the derivative with respect to x. So if we take the derivative of the delta function, well, that's just d by dx of something that looks like this. Of course, that's equal to the delta function. Okay. Are we on board? So in our first example, we found the Green's function was just a step function, or the theta function. I'll call it the step function. But the step function actually satisfies that identity that the linear operator acting on the Green's function should give us a delta function. Well, let's try another. Let's try L equals d squared dx squared. Okay. And again, we're going to act on y with it, with some function that's going to be forcing things on the right. And this time we have to provide two boundary conditions. And I'm going to start with the boundary condition that y of a is y0. And I'm also going to give a boundary condition on the derivative of y at a. And I'll just call that y twiddle 0. Okay. So, well, we can do the same thing that we did before. We can actually integrate this. And so if we do the first integral, then what we'll find is that dy dx is y twiddle 0 plus the integral from a to x of f of x prime dx prime. Okay. And then we can integrate again. And what we'll find is that y of x is y naught plus y twiddle naught times x minus a plus the integral from 0 to x dx double prime integral from a to x double prime of dx prime f of x prime. Okay. Now, I would like to know who is willing to buy this. I can actually do a little bit of massaging of this last term into a following form.
Wait, I have a clarifying question. Which of the primes here are like derivatives and which are
None of the
like
primes-
this is
none
a
of the-
different?
None of the primes are derivatives. So when I have a derivative, I'll write it as d by dx. The primes are just, they're alternate labels.
Okay, thank you.
Sorry about that. So I can massage this last term into the following form. Sorry. Okay, who's willing to buy that? Who feels comfortable with that? It involves an interesting reassignment of the bounds of the integrals. You're kind of moving the argument of the integration around. Everybody buy that? I didn't think so. It's actually true, and you won't prove it to yourself in your homework, but you'll look at a couple of examples to make sure that that's actually a legit action. I find actually that there's an explanation for why you could do this in the book, but it's really hard for me to wrap my head around, and it's much easier to just test it by taking a simple function and then doing these two integrals and seeing, or doing these two sets of integrals and finding out, yeah, I get the same thing every time. Okay, so now we can do a little bit more massaging. And we can say, okay, this is going to be y naught plus y naught twiddle x minus a plus the integral from a to x. Oh, wait, I can integrate dx double prime. So this is just going to be x minus x prime f x prime dx prime. Okay. But that's just going to be well, hold on. Can I switch the integral from a to x to an integral from a to b? What would I use if I wanted to do that?
Theta function.
I'd use a theta function. So this is going to be x minus x prime times theta, x minus x prime, f of x prime, dx prime. And that should give me the solution to the differential equation. Therefore, what is g of x, x prime in this case? Danny. Danny, you're going to sway until you answer. Is Danny on? Danny's not on. I don't see Danny. Okay, well, we'll try Jacob.
So it should just be x minus x prime times theta. Or is that right?
Yes,
Can you hear
yes,
me?
sorry, I was looking on my paper to figure out where the solution was, and I was right.
Okay.
Yeah, so x minus x prime times theta x minus x prime. Okay. So yeah, that's that's a little bit more complicated. Let's check our condition that L on G should be delta x minus x prime. Okay. So we've got d2 dx squared on x minus x prime theta x minus x prime. Well, we can take the first derivative, so we'll be left with d by dx of, take the derivative of x, that's just 1. And then if we take the derivative of a step function, then we get a delta function. What is this term right here? Scott. Got on? Scott's not on. Scott's got to be on. Nope, Scott's not on. Andrew,
Is it 0?
why would it be 0?
Yeah, I'm not really sure.
Well, what is the argument of a delta function in order for it to be non-zero?
The point, the
Sorry?
x prime for here.
Yeah, it has to fix x equal to x prime for the delta function to be not 0, but what's the coefficient of that if x is equal to x prime?
Oh, 0. Yeah, I see it now.
0. So
Yeah.
this is 0. So this means that this reduces to d by dx of theta of x minus x prime, but we've already talked about the fact that that's a delta function. Okay? So it seems like the whole L acting on the Green's function gives you a delta function is actually working out. And there's one more detail that I want to throw into this, but I'm going to not write it up. It's actually written in the notes that I'll post on the website. But you'll notice that in both of these examples, I gave you boundary conditions, which were basically initial conditions. It turns out that the Green's function that you get based on an operator L depends not just on the operator L, but also on what boundary conditions you're planning to specify. So in both of these examples, I gave you initial conditions. However, we could consider, it's a second order differential equation, so we need 2 boundary conditions. We could consider giving you the initial value of the function y and the final value of the function y. No derivative condition, just the bounds on the function y. That would be 2 boundary conditions which we could apply. So it turns out that in deriving the form of the Green's function, it depends not just on the operator, but on the form of the boundary conditions that we're supplying. And like I said, I've written up an example in the notes, and you can see that based on the course website. But I don't want to keep going with this. I would rather get our feet wet in a more general context. And there's a what's going on in the chat room? Oh, never mind. Okay, all right. Go away. There we go. Okay. All right. So now, to be more general, what we're going to do now is we're going to consider an operator which is of the following form. Okay. And of course, this is going to be acting on a function y, on an unknown function y, and it's going to be equal to a function f. And this time we're going to take x to subside on the interval from -infinity to infinity. Okay. Now, what I'd like to do in this case, so this is going to be a much harder evaluation of what the Green's function is, but you'll see what we can do to find it in just a minute. But first of all, I have to make a few assumptions. So my assumptions will be that f of x, y of x, and the derivative of y with respect to x all go to 0 for any x, or for the magnitude of x going to infinity. Okay? Now, the reason we want all this to happen is to open up the door to the next interesting application, and that is to do a Fourier transform of each and everything in this equation. So if we do that, if we Fourier transform the left-hand side, then we're going to have 1 over root 2 pi integral from -infinity to infinity of d2 y dx squared plus a dy dx plus by e to the ikx dx. Okay, that's the Fourier transform of the left-hand side of this expression. And then, of course, we can Fourier transform the right-hand side. 1 over root 2 pi integral from -infinity to infinity of f of x e to the ikx dx. All right. Now, I want to stress to you, because I'm going to give you a problem in your homework, which is basically going to walk through these steps, but you're going to be starting with a slightly different expression. Here we go. So first of all, we can do an integration by parts of this guy and this guy together. They're multiplied together, obviously. So if we integrate this by parts, then what we'll end up getting is dy dx times e to the I kx, evaluated from minus infinity to infinity, minus the integral from minus infinity to infinity of dy dx times the derivative with respect to x of e to the I kx dx. Okay. So first of all, what is the boundaries, the boundary terms? That's the term in the square bracket evaluated from minus infinity to infinity. Seth.
One.
It's one. What makes you think that this is one?
It's periodic. So we're looking at the average over negative infinity to infinity.
Well, e to the I kx is not the only part of this. You also have dy dx. And what assumption might we have made about that?
Yeah, it forces it to go to 0.
Yes. So this guy is going to be 0. Okay. So all we have left is this guy. And of course, that integral is pretty easy to do. Minus oh, sorry. Yeah, I was confusing the crap out of myself because I was like, that's not an integral, that's a derivative, but I'm taking the derivative of this first. So I get integral from minus infinity to infinity of dy dx e to the I kx dx. Okay. So then what we have, taking this result and plugging it back in here, is the following. 1 over root 2 pi integral from minus infinity to infinity of a minus I k times dy dx e to the I kx dx plus 1 over root 2 pi integral from minus infinity to infinity of b y of x. My goodness. E to the I kx dx. And that is, of course, equal to 1 over root 2 pi integral from minus infinity to infinity of f of x e to the I kx dx. Okay. Well, now we can do the same integration by parts on this combination of a term and an exponential. And if we do this, then what we're going to get is, of course, y times e to the I kx evaluated from minus infinity to infinity, which in this case is going to give me what? Any takers?
0.
Yeah, it's going to give me 0 again because y has got to go to 0 as x goes to infinity. And then from that, we're going to have minus I k integral from minus infinity to infinity of y e to the I kx dx. Oh, sorry. Hold on just a second. Oh, Lordy, something went wrong in my notes. So let me peruse this and sort it out. Oh. No, sorry, this is right. Yeah, this is right. Yeah, I went ahead and took the derivative of the exponential. That's what I thought I had left out. Okay, so now we're going to shove this result back in, and what we're going to find is the following, and this is where it gets interesting. We get something that looks like the following: minus k squared minus iak plus b, acting on what we could call the Fourier transform of y. Okay, so y hat is just 1 over root 2 pi integral from minus infinity to infinity of y of x e to the I kx dx. And that, of course, is equal to the Fourier transform of the function f. Goodness. Okay. Now, this is where we can do something rather interesting, which we could not do before when these were differential operators acting on the function y. That set in square parentheses, that's a set of numbers. We have a set of numbers times something equals something else. What can we do with that set of numbers to get the y by itself?
Divide.
Man, Sam, thank you for that very quick response. You sounded a lot like Ross. It's crazy, but you kind of look like Ross. So
Sorry.
Yeah, no, I'm kidding. I'm kidding with you. So we got y of k, y hat of k is f hat of k divided by these things, which are just numbers. So we can certainly do division. Oh my goodness, I'm gonna have to figure out what's wrong with this. Okay. But now we can start unpeeling these Fourier transforms. Okay, we did the Fourier transforms and we did the integration just in order to get these as numbers in front of the y function so that we could divide them over. But now we can undo that by undoing the Fourier transformedness of it. So let's start with the Fourier transform of fk. So if we restore that, then what we'll find is the following. Actually, no. So the first thing I'm going to Fourier transform is the y. So we're going to take the y back to y in the x space. And so in doing that, we know we're going to do 1 over root 2 pi integral from minus infinity to infinity of f hat of k over minus k squared minus iak plus b e to the minus ikx dk. Okay, so there's our inverse Fourier transform taking y of k back to y of x. And now we can undo the Fourier transform on f itself. And this is going to lead us to 1 over 2 pi times the integral from minus infinity to infinity of dx prime times the integral from minus infinity to infinity of f of x prime e to the I kx prime. Oh man, go away. Over minus k squared minus iak plus b e to the minus ikx. Okay. And this is integrated over dk, sorry. Oh, well, wait a minute, hold on. What if, yeah, so if I stare at this expression long enough, can we glean what the Green's function is in this case? Max.
Alex, I want to say e to the ikx prime, e to the negative ikx over your numbers.
Over my numbers, yes, but there's an extra integral in there. Right? I mean, because in defining our G, we just want a single integral. So what we'll find is that the Green's function in this case is 1/2 pi integral from minus infinity to infinity of, as he mentioned, e to the minus ik x minus x prime all over minus k squared plus iak, and that should be minus iak, plus b.
Why does the Green's function include the Fourier transform, since it's something you sort of added after the fact? If that makes sense. Like you did the Ly equals f and then took a Fourier transform of each side. So why does that Fourier transform get included in G?
So remember how we define our Fourier transform. Let me go back to yeah, there we go. So we can look at it here, for example. So y of x is going to be the integral over the domain of x times the Green's function times the function times dx prime. Okay, so sitting here in this expression here, okay, I want the integral dx prime gx x prime. That's what I want to identify. Does that make sense?
Okay.
Okay, all right. I don't know if you sounded that convinced, but nonetheless, sometimes this is going to carry over integrations that are left over from the Fourier transforms and the inverse Fourier transforms. Okay, so all right, well, this, it doesn't look that hard of an integral to do, right?
Alex, can I ask you a question?
Sure.
So earlier when you defined the Green's function, you had a summation of eigenvalues, or well, eigenfunctions, I should say.
Yes.
And now you have an integral over things which look
Yes.
like eigenfunctions. What's the same and different in these two situations? So I just thought of an idea. Would it be the fact that you're working on an infinite domain?
I believe that is the case. And if we made the domain finite, I'm not actually 100% sure. Let me. I don't have a good answer for you right now, Joel.
Okay, that's fine.
Yeah, so unfortunately, the scheme we're working in now is what we're going to be working in henceforth, but relating that back to the eigenfunction expansion it'll take some thought on my part, but let me press on because we're already running out of time and I've got another 4 pages of notes I'm supposed to go over. So as usual, I'm well behind. But let me first rewrite this guy in the following fashion. So I can write this as minus 1 over root 2 pi, or 1 over 2 pi, integral from minus infinity to infinity, e to the minus ik, x minus x prime, over k minus k plus times k minus k minus. Goodness, this is driving me nuts. K minus dk with k plus and minus equal to plus minus b minus a squared over 4 square root minus ia over 2. Okay? So no, that's not at all obvious, but you can massage it out of that by actually working backwards. And first and foremost, notice this integral has a couple of singularities. Those singularities, they sit in the plane in the negative part of the complex plane, because the imaginary part of these is negative, and one is to the right and one is to the left of the real axis. So we have a situation with 2 singularities that look like that. Okay? Now the integral that we're doing is over the real values of k from minus infinity to infinity. So what we would like to do is somehow evaluate that integral, but it's going to be defined in the complex plane. So this is actually begging for us to employ some of the tactics that we just finished learning in our study on analytic functions. So here we go. Let's evaluate that integral. And I'm going to dress up my picture of the complex plane for a moment. So we're going to have a complex plane, which is actually the k plane. This is the plane in which the complex values of k sit. And we're going to have a value we'll call k plus and a value we'll call k minus. And then what we want to do is we want to utilize a contour. So in order to use a contour, we can first of all just draw a line from, and this line is degenerate with the real axis. I'm just drawing it a little bit below so it doesn't overlap. And what we're going to do is we're going to create a closed contour by continuing this on the bottom. And we'll take the contour to be clockwise. So this is going to be the r cut off on the real axis minus r cut off on the real axis. And now what we can imagine is if I took r in this contour integral to be infinity, then a contribution to the integral would be the integral from minus infinity to infinity along the real axis. So there's something hiding in here that is going to let us evaluate that integral, but we've got a couple of other parts we have to mess with. So let me first of all write down the integral around the closed contour, which is e to the minus I k x minus x prime over k minus k plus k minus k minus dk. Now, I want you to notice that is not the integral that we want to do. The integral we want to do is the integral over the reals from minus infinity to infinity, but we can break this contour integral up into 2 pieces. First of all, we can break it up into the contribution from the real axis integration, so integrating from minus r to r of e to the minus ik x minus x prime all over k minus k plus k minus k minus. And then we can actually parameterize this half circle path in the usual polar language for a complex variable. So we're going to have 1 over 2 pi integral from 0 to minus pi of e to the minus I r x minus x prime e to the I phi, and that e to the I phi is sitting in the exponent. All I've done is I've taken k and I've written it as r e to the I phi because k is complex. And then we have I r e to the I phi. This comes from transitioning the dk over into the d phi. And then this will be r e to the I phi minus k plus r e to the I phi minus k minus. And all of that is now integrated over d phi. So this is just the integration along this half circle portion of the path, okay? Now notice the limit of this is what we want. Okay, that's this contribution right here. So in order to get that, what I can convince myself of is if I could figure out this term for the complete closed contour integral and the contribution from here, then that's enough for me to figure out what this thing is. Well, let's start with the closed contour. Actually, no, hold on. I think, actually, I'll start with this just to be quick. So if I take this guy right here and I consider the limit that r goes to infinity, then it turns out that this is equal to 0 by something called Jordan's lemma. Okay, now that was actually in the analytic functions chapter, but it was in a section that we didn't get to go over, so I'm not going to try and cover that right now. But that guy is going to go to 0. So when the limit as r goes to infinity, this guy right here is going to be the same as what we have in the closed contour. Well, in the closed contour, clearly we have the closed contour integral of a function around two singularities. If I'm integrating around a closed contour, and that closed contour contains singularities, what can we relate the integral around the closed contour to? Any takers?
The integral about singularities.
Yeah,
You
what do we
can
call
integrate.
that?
The residual.
The residue, yeah.
Residue, my bad.
That's okay. Okay, good job, Joel. All right, so the integral that we're after, goodness, is 2 pi I times the residue. And the residue, what we do, so this is the residue from the k plus, and this is the residue from the k minus. And the way that we evaluate the residue is we say, okay, I'm going to do minus 1 over 2 pi I times the integral around a contour, one for the plus and one for the minus. And the contour is basically a contour which is small enough to contain a singularity that you're trying to integrate to find the residue of, but not the other, okay? So C plus minus includes K plus minus, but not K minus plus, okay? Now, the reason we want that is because I can write this integral in the following form, e to the minus ik x minus x prime over k minus plus which is all over k minus k plus minus. Now, that's a really simple rewriting of the integral. But I want you to stare at that for a moment, and I would love for Lucas to tell me what is so nice about the numerator of this larger fraction.
Oh, hold on. Can you hear me now?
Yeah.
Let's see. Aside from it going to 0? Wait.
So let's take the C plus contour, which goes around the plus option. Well, I lost my plus. If I take the C plus option, e to the minus ik x minus x prime, that's not going to do anything funny. What about k minus k minus? Or sorry, yeah, k minus k, wow, k minus just rolls off the tongue. K minus, is that going to go to 0 anywhere in this contour? So we're doing the contour around this. K minus will go to 0 when k is equal to this. So is this denominator here ever going to be 0 throughout this contour integral?
It shouldn't, because that would make the whole thing go to 0.
Right. So what can you tell me about this numerator in terms of its differentiability and analyticity? Is it an analytic function?
Right. It should be both differentiable and therefore analytic.
Yes, this is analytic within this circle. It's not analytic throughout this entire red path because that includes this point k minus. All right. So what we have is an analytic function over a divergent contribution from the singularity. Okay. But the Cauchy integral formula tells us how to deal with that. Remember, the Cauchy integral formula says that if I want to do an integral of 1 over 2 pi I times an analytic function over z minus z naught, where I'm doing a closed contour around the point z naught, then that is just equal to the function evaluated at the singular point, z naught. Okay? Now, notice this wz naught, this is not going to be infinity because wz is analytic at the point z naught. This entire integrand is not analytic because the denominator is z minus z naught. That's going to blow up. But the function wz is analytic. Does this make sense? You're all quiet as mice. It's fine. I'll just take that as a tacit, yes, this totally makes sense. Therefore, to evaluate the residues r plus and minus, all we do is we take this function in the numerator and we evaluate it at k plus and k minus. So r plus minus is going to be minus e to the minus ik plus minus x minus x prime over k plus minus minus k minus plus. Okay? Now, if I massage that a bit more, I can get that into the following form: minus plus 1/2 e to the minus. And now what I'm going to do is I'm going to substitute back in what this k plus and k minus were defined to be. So I'm going to get e to the minus a over 2 x minus x prime, e to the minus plus square root of b minus a squared over 4 times x minus x prime, all over the square root of b minus a squared over 4. Okay. We're just using these definitions here. All right, now what we actually need is not r plus and minus separately, but rather we need the sum of the two of them. And that is a bit of a simplification. And I will skip some of the steps. They're outlined in the notes, but I just want to try and get along because we're going to be done in 5 minutes. But what we want to do is we want to simplify this, and we find it takes the following form: I e to the minus a over 2 x minus x prime all over the square root of b minus a squared over 4 times the sine of the square root of b minus a squared over 4 times x minus x prime. Okay? Now, wait a minute. So the integral that we were trying to do, sorry, I didn't write down what I was. Oh, yeah. I think I wrote it down. Did I write it down? Oh, no. I'm going too far back. Oh, yeah, here it is. I. Sorry about that. So I is just minus 1 over root 2 pi times this. So in the end, what we can say is that I, which is going to be equal to the Green's function, is equal to e to the minus a over 2 x minus x prime over root b minus a squared over 4. Good God, it's driving me nuts. A squared over 4 times the sine of b minus a squared over 4 times x minus x prime. For x larger than x prime. Okay. Now it has to be, x has to be larger than x prime because that's actually a condition that has to be satisfied in order for this Jordan's lemma to hold. If we don't have Jordan's lemma, then, well, I mean, if x is greater than x prime, what could we do? X is less than x prime. Oh, ooh, I know what we can do. If x is less than x prime, I promise I will figure that out and fix it. Then we can use a different contour. Where we go from minus r to r, and then we go in the upper half plane. Now recall our singular points are down here. The Green's function is going to be equal to the contour integral around this whole thing because in the upper half plane, when x is less than x prime, Jordan's lemma is going to hold, and it's going to take the integral around the circular arc to 0 as r goes to infinity. But we have to figure out what the integral around this entire contour is. We use the residue method to figure it out in this case. What is the integral around that closed contour going to be in this case? Any takers?
Is it going to be 0?
Why?
Because it's analytic.
Yes, we're integrating an analytic function on a closed contour, throughout which that function is analytic. So for x less than x prime, gx x prime is 0. Okay? So in the end, we have the following. The Green's function, gxx prime, is we're going to install an theta function to guarantee that we get 0 when x is less than x prime. And then we just get the result that we've already got down, but I'll write it one more time. There's our Green's function. Okay. Now, it's 6:15, so I think I'm going to go ahead and end, which means, of course, that I'm going to shortchange my goals for the last 3 lectures, but that's fine. I am going to ask you to take this expression for the Green's function in your homework and verify that it does in fact satisfy that the linear operator which we started with acting on it gives you a delta function. Okay. When we come back on Thursday, we will not yet be jumping into 3 dimensions, but rather what we're going to do is we're going to complete this analysis of the solution, and then we're going to apply it to at least one example, okay, so that we can see how this is working out, and then we'll wade our way into 3 dimensions or higher. Sorry, my pace was so slow, but writing on a screen is kind of odd. I think I'm a little bit quicker on a whiteboard, but you know, it's a less physical activity, this writing on the white screen thing is. Are there any questions before we go today?
I do have a question.
Sure.
Will you be able to make it this Friday to SPS?
Yeah, I'm thinking I will. Yeah, and I know I haven't responded yet, but that's because I was having a hard time figuring out what I was going to talk about.
Oh, that's fine, yeah.
But I have a back pocket topic to talk about, which I think I probably have mentioned it to you guys before, but I think it's good to mention it to the younger people because they're about to get taught the wrong thing. And I would like to go ahead and warn them that what they're going to be taught is wrong.
Is this the classic planes versus axes rotations?
Yes.
All right.
Unless you find that boring, in which case I won't come. I'm going to have to go
No,
to
I
dentist.
actually really like that. That actually did help me out with a few things in the future.
Yeah, well, it's interesting because, by the way, you guys, you're all free to go. So we're just having a conversation at this point. But at any rate, yeah, Dan Adams sent me an email asking me about how is it that 2 vectors cross product gives you a pseudo vector? I really don't understand that. And I explained it to him and he was like, oh, wow, I've never seen that before. So yeah. So we'll break that isometry between normal vectors and planes and how poorly constructed that is in another number of dimensions.
That'd be lovely. That's a fun topic.
Yeah. All right. Thanks you all for putting up with me. I realized it probably hurt a little bit, but you know, it'll hopefully be a little bit better next time.
Honestly, the screen is so much easier to read. Like, it is so nice.
I'd actually agree with that.